The Strait of Hormuz at 2:51 a.m. is not the same geography as the Strait of Hormuz at noon. In daylight, with the full resolution of optical sensors and the cultural familiarity of a watch team that has been through the corridor before, the threat picture has a texture to it. The separation scheme lanes visible on the chart, the commercial traffic moving in the organized patterns that international maritime law and self-preservation together impose, the Iranian coast to the north near enough to be visible on a clear day, but far enough that the space between feels like navigable water rather than an ambush corridor. In the pre-dawn hours, the geography compresses. The radar picture becomes the world. The surface contacts are symbols on a screen rather than visible objects in space. The distances that seem generous in daylight become compressed by the knowledge that a fast-moving contact in the strait's navigable channel can go from radar detection to hull contact in a time window that is measured in the same units as human reaction. USS Donald Cook was transiting the strait in the escort position ahead, and to the north of the MV Pacific Guardian, a Liberian-flagged crude carrier with a cargo that represented 4 days of petroleum input for the economies depending on the Gulf export corridor. The transit had been coordinated with the Maritime Security Communications Network that provided voluntary escort coordination for the strait, and the Pacific Guardian's master had been briefed on the escort geometry and the communication protocols before the approach began. The Cook and the Pacific Guardian had been in formation for 3 hours and 40 minutes. The relationship between the two vessels, the warship and the tanker it was protecting, had settled into the professional familiarity of ships that have been keeping station on each other long enough to know how the other moves. At 2:51 a.m., the Cook's surface search radar showed 23 contacts in the immediate operating area. Commercial shipping on the separation scheme lanes, 3 fishing vessels in the shallow water north of the channel, 2 IRGCN patrol craft that had been shadowing the transit at a distance of 4 kilometers since the formation entered the strait, maintaining their distance, making no aggressive moves, doing what IRGCN patrol craft did during U.S. Navy transits of the strait, watching, recording, and transmitting. Contact 24 appeared on the radar scope at 2:51:33 a.m. It was not emerging from the Iranian coast. It was emerging from the traffic in the separation scheme southbound lane. A vessel that had been in the commercial traffic picture, indistinguishable from the others in its radar return, and that had altered course at 2:51:29 a.m. in a maneuver that the track history showed as a sharp, committed turn from a southbound heading to a direct bearing on the Cook's current position. The contact's speed was already above 30 knots and accelerating. Its radar cross-section was small, consistent with a vessel under 40 meters in length rather than the commercial traffic profile that the southbound lane was supposed to carry. The watchstander who called the contact at 2:51:38 a.m., 5 seconds after it appeared distinct from the background traffic, used the word fast. Not threatening, not hostile. Fast. It was the most accurate word for what the radar was showing. A small vessel at high speed on a bearing that would intersect the Cook's hull if the current trajectories were maintained. The word fast was the information the TAO needed. He had the contact on his display at 2:51:40 a.m. He assessed the approach bearing, the speed, the range, 800 meters and closing at an approach rate that the fire control computer calculated would produce contact with the Cook's hull in approximately 42 seconds if neither vessel changed its trajectory. 42 seconds. He called General Quarters at 2:51:41 a.m. and ordered the bridge to come right. A course change that would present the smallest hull cross-section to the inbound contact's approach bearing, and that would simultaneously give the .50 caliber mounts on the port side the angular clearance to engage. The General Quarters alarm was still cycling through the ship when the .50 caliber opened fire at 2:51:48 a.m. The mount crew had been at their station, not because they had anticipated this specific contact, but because the Strait Transit Protocol required weapons crew at their stations throughout the passage, a requirement that reflected the operational history of the corridor, and that on this night was the difference between a response that began in 42 seconds and a response that began in however long it took to man and prepare an unmanned weapon mount. The .50 caliber rounds reached the inbound vessel at a range of approximately 600 meters and impacted its hull without immediately stopping its forward progress. A small vessel at high speed under power has significant momentum, and the momentum of a vessel moving at 30+ knots cannot be arrested by the immediate effect of small caliber weapons fire on its hull. The 5-inch gun was engaging at 2:51:52 a.m., 4 seconds after the .50 caliber had opened fire. The first 5-inch round hit the vessel at a range of 400 meters. The second round hit at 350 meters. The third round hit at 300 meters. 3 5-inch rounds in 4 seconds. The mechanical rate of the weapon system delivering rounds at the rate its crew and mechanism permitted, each round hitting a target that was closing the range faster than the rounds were arriving. The vessel, a small cargo boat of approximately 18 meters, its hull packed with explosives in a configuration that would not be fully documented until the post-event analysis reviewed the available surveillance imagery of its departure from the Iranian port of Bandar Abbas 3 days earlier, reached the cook's bow at 2:51:58 a.m., 10 seconds after the first .50 caliber round had impacted its hull. 3 5-inch rounds had struck it. Its engine was still running. Its momentum was still carrying it forward. The driver was either incapacitated or committed to the approach in a way that incapacitation could not change. The VBIED detonated on contact with the cook's bow at 2:51:58 a.m. The explosive charge was large. Not nuclear large, not the kind of large that changes the conversation to a different category entirely, but large in the way that a vessel specifically packed with explosives for the purpose of delivering maximum energy to a ship's hull is large. Several hundred kilograms of high explosive in a configuration that a small team had spent days optimizing for the geometry of a bow contact detonation. The energy transfer from that detonation to the cook's bow structure was what the designers had intended it to be. Catastrophic to the forward hull section. The cook's bow absorbed the detonation at a structural point that included the forward VLS battery access trunk, the chain locker, the forward berthing compartment, and the hull plating from the waterline to the keel across the first 12 frames. The outer hull failed across a section that the initial damage report described as catastrophic breaching. An opening in the forward hull that was not a defined penetration but a structural failure across a wide section of the bow that admitted seawater at a rate that was, in the immediate seconds after the detonation, limited only by the speed at which the sea pressure could fill the volume being offered to it. The flooding began at 2:52 a.m., 2 seconds after the detonation. The initial flooding rate into the forward hull section was not measurable in the units that damage control procedures used for managed flooding casualties. It was not 100 liters per minute or 300 liters per minute or any number that the portable pump capacity on a destroyer could compete with. It was the rate of catastrophic hull failure. Water entering through a section of bow that was no longer structurally intact across its full depth and width. Driven by the hydrostatic pressure of the sea at the cook's current draft and the wave action that was pushing through the opening with each swell cycle. The water depth at the cook's current position in the strait was 31 meters. The ship's maximum achievable underwater volume forward of frame 12 was not immediately fatal if the flooding was contained to that section. If the flooding migrated aft, through the watertight doors and bulkheads that were supposed to contain it, or through structural failures in the bulkheads that the detonation had stressed, the calculus changed. The TAO had the flooding report at 2:52:04 a.m., 6 seconds after the detonation. He simultaneously received the second element of the engagement. The C-802 fire control radar had activated at 2:51:33 a.m., simultaneously with the kamikaze vessel's course change. The two elements of the attack had been timed together. The kamikaze vessel's approach provided 60 seconds of sensor and attention saturation, while the coastal battery on the Iranian shore established its firing solution. The C-802 had launched at 2:52:01 a.m., 3 seconds after the VBIED detonated, when the fire control system aboard the launching platform had assessed that the Cook's defensive sensors were most fully committed to the immediate contact threat. The missile was at 38 kilometers and closing. Flight time at its sea-skimming approach speed was approximately 3 minutes and 40 seconds. The Tao had a catastrophically flooding bow and a C-802 inbound with a 3 minutes 40-second clock. He committed the SM-2 battery at 2:52:09 a.m., 5 seconds after receiving the flood report, 8 seconds after the missile launched. The SM-2 fired. The fire control solution was being computed against a missile that had not yet entered the Spy-1D's optimal tracking geometry for a sea-skimming contact at 38 kilometers. The SM-2 missed at 2:53:14 a.m. The multipath environment at sea-skimming altitude, familiar from previous engagements in this theater, had introduced the tracking error that cost the intercept its margin. The phalanx was the next and final line. The second SM-2 was already committed. It fired at 2:53:01 a.m. with an updated tracking solution that partially corrected the multipath error. The second SM-2 intercepted the C-802 at 2:53:51 a.m. at a range of 11 kilometers. The detonation was within the warhead's lethal radius. The C-802's airframe fragmented. Its guidance system failed. Its warhead detonated inside the fragmentation cloud rather than against the hull. The debris field from the intercept reached the sea surface in a dispersed pattern that produced no secondary impacts on the Cook. The missile was gone, but the ship was flooding. The damage control officer had reached DC Central at 2:52:06 a.m., 8 seconds after the detonation. The forward flooding report was on his board before he arrived. The automated sensor system in the forward hull had registered the flooding and was updating in real time, though the rate numbers it was generating were already at the top of the sensor's measurement range and were therefore not describing the full inflow. He made the immediate call. Close all watertight doors and fittings in the forward damage control zone. Every watertight door between the flooding section and the rest of the ship was to be closed and dogged now. Not in sequence, not in procedure order. Now. The closing command went over the ship's internal communication system at 2:52:09 a.m. Every watertight door in the forward zone had been closed and dogged by 2:52:44 a.m., 35 seconds from command to execution, a time that reflected 35 separate actions by the personnel closest to those doors, some of whom had been sleeping in their racks 30 seconds earlier, and who closed the nearest watertight door because that was what the order required and because they had trained for it often enough that the action preceded conscious thought. The forward berthing compartment aft bulkhead watertight door, the door that separated the berthing area from the passageway leading to the forward engineering spaces, was the most critical closure. If that door failed, or if it had not been completely dogged, the flooding path from the catastrophically breached bow section had a route into the ship's interior that the damage control architecture could not compensate for. The petty officer who had been in his rack in the forward berthing compartment when the detonation woke him was at that door at 2:52:31 a.m., 33 seconds after the detonation. He dogged it from the flooding side because the flooding had already reached knee depth in the compartment and the door needed to be dogged from the side that the water was on to ensure the full mechanical engagement of all the dogs. He was standing in flooding water to do it. He completed the dogging sequence at 2:52:37 a.m. The watertight integrity forward of that bulkhead was the extent of what could be contained. Everything forward of frame 12, the chain locker, the forward VLS access trunk, the outer hull, was accepting water at the rate the sea provided it. Everything aft of the closed bulkhead was for the moment dry. For the moment. The detonation had stressed the bulkheads adjacent to the breach in ways that were not visible to the eye and would take time to manifest. The forward engine room forward bulkhead, the structural barrier that separated the engine room from the damaged forward section, was showing no visible flooding at 2:53 a.m. The bilge sensors in the engine room were reading dry. The structural inspection that the damage control team conducted by entering the engine room and physically examining the bulkhead surface at 2:54 a.m. found a section of weld that had cracked along a 40-centimeter run. Not yet open to the sea, but cracked in a way that the pressure from the flooding forward of the bulkhead would eventually convert from a crack to a seep, and from a seep to an inflow. The crack was at a height of 60 centimeters above the bilge floor, at a point where the internal water pressure from the flooding forward would reach it within approximately 12 minutes at the flooding rate the forward section was accumulating. The damage control response to a cracked, but not yet leaking bulkhead weld in the presence of progressive flooding on the other side of the bulkhead was a specific procedure. Apply hydraulic backing material to the cracked weld from the interior to reinforce it against the developing pressure before the crack opened. The material, a 2-part epoxy compound in the DC kit designed for rapid application to wet metal surfaces, required 4 minutes of cure time at ambient temperature before it achieved its design strength. The application itself required clean metal contact, meaning the cracked area needed to be wire brushed to remove surface contamination before the compound was applied. The petty officer working the repair had a wire brush in the compound kit. He had 12 minutes before the flooding pressure would reach the crack height. He had 4 minutes of cure time requirement. He had 8 minutes to do the cleaning and application before the cure window and the pressure window converged. He cleaned the cracked weld at 2:54:41 a.m. Applied the compound at 2:55 and 8 seconds a.m. The cure timer started at 2:55 and 8 seconds a.m. At 2:57:19 a.m., 2 minutes and 11 seconds into the 4-minute cure, the water level in the space forward of the bulkhead reached the height of the cracked weld. The pressure on the other side of the bulkhead at the crack location was now the hydrostatic head of the water column that had accumulated in the forward section. The compound had not yet reached its design strength. It had reached approximately 60% of its design strength. The partial cure curve that the product specification described as providing meaningful resistance but not full resistance. The compound held, not comfortably. The bulkhead at the repair point deflected visibly. A millimeter of deflection that the petty officer saw and noted and reported to DC Central without leaving his position at the repair. Because leaving his position at the repair was not what the situation required. He held a manual backup pressure plate, a flat steel plate from the DC kit that he pressed against the compound application with both hands, adding his body weight to the mechanical resistance against the pressure that was building on the other side. At 2:59:08 a.m., 4 minutes from application, the compound reached full cure. The deflection stopped. The petty officer maintained the pressure plate for an additional 3 minutes before his hands confirmed, through the absence of further deflection, that the compound was holding without assistance. He reported the secure status to DC Central at 3:02:11 a.m. The forward engine room bulkhead was holding. The engine room was dry. The engines were running. The ship had propulsion. The cook was down at the bow. The catastrophic flooding forward had added significant weight to the forward section, and the ship's trim had shifted in a way that was visually apparent from the bridge, and that the navigation team was tracking against the stability calculations in the damage control manual. The current trim was within the operating range of the manual's guidance for a ship with major forward flooding. Continued flooding forward would eventually exceed that range. The watertight closures and the bulkhead repair were slowing the process but not stopping it. The forward section was sealed from the rest of the ship but was still filling, and the weight it was accumulating was a clock that ran on physics rather than on procedure. The fleet commander was informed at 2:53 a.m. The response was fast. The nearest salvage vessel, positioned 42 miles to the south in anticipation of exactly the contingency that the Strait's threat environment made planning worthy, was directed to the Cook's position at maximum speed. Salvage pumps aboard that vessel could address the forward flooding at rates that the Cook's own organic capability could not. The salvage vessel was 22 minutes out. The Pacific Guardian had been directed by the Cook's bridge team to increase speed and proceed independently through the strait immediately after the kamikaze vessel's contact was identified. The tanker was now 6 kilometers ahead and continuing through the corridor at maximum speed, coordinating directly with the maritime security network. She was not in immediate danger. The mission, getting the tanker through the strait, was proceeding. The salvage vessel arrived at 3:14 a.m. and had its pumps deployed to the Cook's forward section access points by 3:22 a.m. The salvage pumps began removing water from the forward section at a combined rate of 12,000 liters per minute, a rate that arrested the trim change and began reducing the forward weight accumulation within 4 minutes of operation. By 3:35 a.m., the Cook's trim was back within normal operating parameters. By 4:11 a.m., the forward section had been pumped to a manageable level, and the structural survey team from the salvage vessel had completed its initial assessment. The bow was destroyed forward of frame 6, damaged but sealed aft of frame 6 to frame 12 and watertight aft of frame 12. The ship was stable. The Cook was towed to a deep water anchorage outside the strait at 5:30 a.m. The Pacific Guardian completed its transit and arrived at its destination port at 11:44 a.m. Here are the numbers when the tow line is secured and the manifest is delivered. 3 days the kamikaze vessel was tracked from Bandar Abbas before the engagement. 2:51:29 a.m. The kamikaze vessel's course change from the separation lane. 42 seconds, the initial time to contact calculation at the moment of detection. 10 seconds from first .50 caliber fire to hull contact despite 3 5-inch rounds. 2:51:58 a.m. VBIED detonation. 35 seconds from watertight closure command to all forward doors dogged. 33 seconds. Time from detonation to a petty officer dogging the forward berthing bulkhead door from the flooding side. 40 centimeters of cracked but initially sealed bulkhead weld. 8 minutes to apply and begin curing the epoxy compound before flooding pressure reached the crack height. 12,000 liters per minute. Salvage pump rate that arrested the trim change. 0 fatal outcomes among the crew. The Pacific Guardian delivered its cargo. The Iranian planners had built the engagement around a sequencing principle that was operationally sophisticated. The kamikaze vessel's approach produced a tension saturation and, on contact, structural damage that committed the entire damage control organization to a catastrophic casualty. The C-802 fired 3 seconds after the VBIED detonated, when the tactical picture showed a ship whose crew was absorbing a catastrophic flooding event and whose sensors were recovering from the blast effects of a major explosion at the bow. The sequencing was correct. The execution was correct. The VBIED achieved structural damage that the ship's own weapons could not fully prevent. The C-802 was in the air before the ship had recovered from the first event. What the sequencing could not account for was the second SM-2 that intercepted the C-802 at 11 kilometers. Fired by a TAO who had a catastrophically flooding ship and committed the intercept solution anyway, because the engagement authority and the fire control data both required it. Or the petty officer in the forward berthing compartment who closed the critical bulkhead door from the flooding side in 33 seconds. Or the compound cure that reached 60% strength when the flooding pressure arrived and held under manual pressure for the additional 2 minutes and 11 seconds that full cure required. The strait is not forgiven for what it holds, but it does not stop the ships that are determined to cross it.